Okay, this is practice midterm number 3, and this is problems 22 through 29 in the Scantron part of the test, which is all multiple choice, fill in the bubble. And we're going to be answering questions on electron pair geometry in this particular sequence of questions, or series of questions. But before we address this, there's a strategy that I want you to employ on the test that will maximize the efficiency of the process. And so we want to look at these. This is the prequel. The prequel to problems 22 through 40. And I want you to do this when you get to this point on the test, is look at the compounds that you're going to have to draw. You're going to have to know, to be able to draw the proper Lewis dot structure with the proper geometry. So it has proper bonding patterns and proper arrangement of bonding and lone pairs on the central atom in order to answer these questions. So what you want to do before you start is draw all of the molecules that are included in problems 22 through 40. There's going to be a lot of repetition. The same molecule is going to come up in some of the next series of questions and the series of questions after that, and only a couple of new ones introduced. And so there is 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules that you're going to need to draw. So get your scratch paper out and draw those 9 molecules. So first, note them on the scratch paper and then draw each one. And so the beryllium dichloride is very straightforward. I don't want to go into how I would draw that because this is following the rules that we already have covered in the written part of the test. So that is not going to be anything new, and this is going to be true for all the molecules with these 2 exceptions, and I'll discuss those in greater detail. So in this case, I have a beryllium dichloride. I've got the perchlorate ion, and since I didn't have any examples with a charged ion on the in the written part, I'm going to have a little asterisk here, so I'll show you how to do it. We'll go over what different we have to do for that. But then I've got carbon disulfide, which turns out to be another linear molecule, and then sulfur trioxide, the neutral molecule, the chlorite ion, which is charged, so I've got the asterisk here, so we'll reinforce that. The antimony tetrafluoride molecule, the ozone molecule, or O3, the tellurium hexafluoride, and the nitrogen trifluoride. These are the molecules you're going to need for problems 22 through 40. So you should be able to draw all of these, and you are able to draw all of those. Do that first. Then you've done all the heavy lifting, and it's going to be a simple matter to routinely answer all these questions. Now, as to the perchlorate ion and the chloride ion, I'll give a brief discussion of how that's done. We would do the same thing we did before. We would start with, because I'm given the formula ClO4 minus, I would start with, draw the chlorine with the 4 oxygens around it, and then I would start adding up electrons. I have group 7, so I have 7 plus 4 times 6 plus 1 equals. So the point is, because of the charge, I have to include that in my initial electron count, and then draw the molecule as we did with all the others in the written part of the test. So this would be 4 times 6 is 24 plus 8, would be 32 electrons. I then would, I would draw a line connecting the central atom to the outer atoms as we did before. Deduct 2, 4, 6, 8 minus 8 electrons. There is 24 electrons remaining. And each of the outer atoms is going to need 6 to complete its octet. They're given that closed shell configuration, which uses up all I needed to know was there are no lone pairs on the central atom. And so that would mean I have 4 E pairs, therefore a tetrahedral E pair geometry and molecular geometry, and I've drawn it their way on my scratch paper. So you'll have to do that for the chlorate, perchlorate ion, and the same thing will be needed for the chlorite ion. Here I've got I'll do it in red. I've got the formula. I've got an ionic compound. I'll start with the chlorine, draw the oxygens around it, and then I add up electrons. I have 7 plus 2 times 6 plus 1 again for the negative charge. In the event that you had a cation, you would subtract an electron. That's the only difference. That's how we accommodate that change. And now I would have, so this is 2 times 6 is 12 plus 8 is 20 electrons. I draw a line connecting the central atom to the outer atoms. I deduct 4 electrons for each such bonding pair. I'm left with 16 electrons. 16 electrons. I have to distribute those to the outer atoms first to complete the closed shell electron count that Lewis demands. That requires 12 electrons. So minus 12, I have 4 electrons remaining. Those I have to place on the central atom, which gives me and we're assuming I've already got all the electrons out on the outer atoms. And now Lewis is satisfied, but what type of E-pair geometry am I following? So I've got what type of E-pair geometry is going to be required for the central atom. I have 4 E-pairs, therefore I'm going to have tetrahedral E-pair geometry. However, there are 2 lone pairs on the central atom, so the E-pair geometry and the molecular geometry are not going to be the same. This is the same condition we encounter with the water molecule. It's going to give rise to a bent molecular geometry. And so that is how I've drawn it up here, the bent, and using the same approach we use and the notation we use for the 2 lone pairs, where rather than have one come out and one go into the board, I just simply place them about like that. And I have a bent molecular geometry. This is enough to answer the questions that we're going to have. So this is scratch paper work. Your scratch paper before you start looks like this. And this is good to go for 22 through 40. Now that we've got that out of the way, let's now do problems 22 through 29. And the first molecule I have to deal with is beryllium dichloride. And I have to identify the electron pair geometry of the central atom and the molecule. Now I've got several options. A being linear, B is trigonoplanar, C is tetrahedral, D is trigonal bipyramidal, and E is octahedral. So given those options, which applies, which one's going to be applicable to the beryllium dichloride? So now we go back over to our scratch paper. We've already done the work. We've got the molecule drawn. And indeed, the beryllium dichloride has 2 pairs associated with the central atom. And no lone pairs on the central atom, but it doesn't matter whether they're lone or there's no such distinction when we're doing E-pair geometry. The 2 pairs requires a linear E-pair geometry. So this one it would be linear, so I would say A. I would fill in the bubble A. on my Scantron. Now, the second molecule we have to deal with is the perchlorate ion, and we've already got it drawn on our scratch paper. It is a tetrahedral molecule with no lone pairs on the central atom. So I've got 1, 2, 3, 4 E pairs. That's going to demand tetrahedral E pair geometry. The E pair geometry is the same as the molecular geometry in this case, and that is option C. The next molecule we have to contend with is carbon disulfide, which we see on our scratch paper I have a carbon double bonded to 2 sulfurs, and I have 2 double bonds. The double bonds each count as 1 E pair, so I have 2 E pairs. 2 E pairs again that demands a linear E pair geometry. So I've got A is the right option for the carbon disulfide. So I fill in the A bubble on my Scantron with my number 2 pencil. Always remember. And now we're to number 25, sulfur trioxide, which is a neutral molecule. And I've drawn the sulfur trioxide over here. This is one of the resonance forms, but it doesn't matter which one you choose. I have a single bond to oxygen, a single bond, another single bond to oxygen, and 1 double bond to oxygen. When you're counting E pair geometry, you make no distinction between single, double, and triple bonds, so that gives me 3 pairs of electrons. 3 E pairs requires trigonal planar E pair geometry, which is option B. And now for number 26, we've got the chlorite ion. And so this we've done over here. This particular molecule has, the central atom has 2 single bonds to oxygen, between chlorine and oxygen, and 2 lone pairs on the central atom. Well, that's 4 E pairs altogether, which requires a tetrahedral E pair geometry in order to get those E pairs as far apart as possible. And so that is tetrahedral, which was C in my options. Now, number 27 is the antimony pentafluoride. And so I've drawn it up here. You can see that this has the central atom with 5 single bonds and no lone pairs on the central atom. So there's 5 E pairs associated with the central atom. 5 E pairs demands trigonal bipyramidal E pair geometry. And so we have trigonal bipyramidals, option D. Number 28, famous ozone molecule, which was more infamous a couple of decades ago, 30 years ago, 40 years ago, but now it's returned to its non-menacing status. The O3 molecule, which we see over here, I've got the central oxygen atom with a double bond to oxygen, a single bond to another oxygen, and a lone pair of electrons on the central atom. The double bond counts as 1 E pair when we're determining E pair geometry. So I have 1, 2, 3 E pairs, which is going to require trigonal planar E pair geometry in order to get the atoms, or the E pairs, as far apart from each other as possible. That is option B. And now for the last in this series, I've got tellurium hexafluoride. And the tellurium hexafluoride we see depicted over here on our scratch paper. And so I've got the central atom, the tellurium atom, has 1, 2, 3, 4, 5, 6 single bonds to fluorine and no lone pairs on the central atom. So each of these single bonds counts as a pair. There's 6 of them. 6 pairs is going to demand octahedral arrangement in order to minimize the repulsion. So I have octahedral, which is option E. And so once we've done all the heavy lifting, which we did on the scratch paper, this is a simple matter to answer this series of questions. And we're going to be using most of these molecules in the next in the series, and even the one after that. So we've done all the heavy lifting. So take your time and do a good job on your scratch paper before you address these problems, and this will be a simple part of the test. It won't take very long at all, because we've all done the heavy lifting already. We're going to be doing that same stuff. We'll be considering different aspects of these molecules for the next series of questions. Okay?